Welcome to your Unit 3, Lesson 10 notes. This video is going to get us into trigonometric equations and inequalities. The skills and learning objectives of this lesson is to find general solutions for trig equations, solve trig equations in multiple angles, solve trigonometric equations in quadratic form, using factoring techniques and technology to solve trigonometric equations and inequalities, and then solve inequalities. So let's go ahead and get started. So in this lesson, we consider trigonometric equations and inequalities. Equations that contain trigonometric functions can be used to answer periodic behavior in our world. We can predict the tides, moon phases, seasons, breathing intervals, and more. A trigonometric equation is an equation that contains a trigonometric expression with a variable that are satisfied only by some values of the variable or possibly have no solutions. Inverse trigonometric functions are useful in solving equations and inequalities involving trig functions, but solutions may need to be modified due to those domain restrictions. So looking at example 1, let's think about this graphically. So if we consider the equation sine of x is equal to 1/2, and we're focusing on the interval from negative 3/2 of a pi to 7/2 of a pi, which is the graph shown below, notice that the x-coordinates where the graph of y equals sine of x intersects with the line y equals 2. Those would be your solutions of that equation. So can you name the 5 solutions? So the 5 solutions looks like it's appearing at x equaling negative 7 pi over 6. I think is our furthest left. Then we would be at pi over 6, 5 pi over 6. Like next one will be at 13 pi over 6, and then 17 pi over 6 would be those solution areas. And the nice thing is we know that each of those are falling at a 1/6 of a pi, right? Because they have each of those tick marks at a 6. So how do we represent all the possible solutions? So we could say that our first set, right, because they're going to occur every period. So this one's going to occur every period here, and then every period here. And then our second grouping, right, we started at the pi over 6, would occur every period from there to there. So we kind of have 2 separate solutions happening for our answer. So we could say our first, so theta 1 could be, let's do the pi over 6 first. So pi over 6 plus 2 pi k or n, whatever variable you want, where again n is an element of the integers. And then our second set of solutions, I'm going to start, instead of starting at the negative 7 pi over 6, I'm going to start at my next positive, which would be 5 pi over 6. Again, would not matter if you started at the negatives because we're rotating it every period. So you can start wherever you want. I like starting with my positive values. Okay, so that's what it would look like graphically. So let's see if we can put it to pen to paper. So if I had the equation 2 cosine x minus 1 is equal to 0, we would solve this equation just like we would solve any natural linear equation. I would add my 1 to both sides. So then I have 2 cosine x is equal to 1. I want to get that cosine x by itself. So cosine x is equal to 1/2. So now this looks like what we were just doing in lesson 9, right? So we need to do the cosine inverse of 1/2 is going to be equal to x. So I need to think about what angle, right? So what angle has a horizontal displacement of 1/2? Well, that would be horizontal displacement, so it means it's higher than it is wider, so pi over 3. So x would equal to pi over 3 if we were living in here. So pi over 3, we're at 1/2. So there is our x, which is the same as our first angle. But take notice that I also have a vertical displacement at 5 pi over 3. So if I keep looping around and go to 5 pi over 3 or negative pi over 3, then I would get another solution. So we could have our first option being at pi over 3. Second option would be at 5 pi over 3. right? Because that's another place that I would have a horizontal displacement of positive 1/2. So now if I want to do the general solutions, I could just add a full rotation in either direction. That's why we would say n needs to be an element of the integers, because that would allow me to do positive and negative rotations. All right, example 3. Solve the equations, give a general formula for the solutions. Okay, so we have the sine of x is equal to negative root 2 over 2. So for A, we have sine of x is equal to negative root 2 over 2. So let's do the inverse. So to solve any equation, you do the inverse of the operation. So the inverse of a sine is do the inverse of sine. So we need to figure out what angle gives me a horizontal displacement of negative root 2 over 2. So sine negative root 2, did I say horizontal? I meant vertical. Negative root 2 over 2. So we got to go down negative root 2 over 2. So that's going to put me in quadrant 3 and in quadrant 4. So now we got to think about what that reference angle is. So that's pi over 4 here, pi over 4 here. So now we have to think about what those angles are. So this angle here would be, what, 7 pi over 4? No, 5 pi over 4. And then this angle here would be 7 pi over 4. So my x is going, or my first x for general form is going to be 5 pi over 4 plus a full rotation in any direction. And my second value of general form for solutions would be 7 pi over 4 plus 2 pi in any direction. Again, n is an element of the integers. And those would be your solutions. Okay, so we don't necessarily need to think about so when we do the inverse, we kind of don't necessarily need to think about I can only be in quadrant 1 and 4 for sine inverse, quadrant 1 and 2 for cosine inverse, because we're getting all the possible solutions that could happen. So where on my continuous graph of sine would I land with a y value of negative root 2 over 2, right? So I would land at negative root 2 over 2 at all those negative values of our angle, but I'm going to cover those negative values by doing this general form. Okay, let's go over to B. So solve it just like you would do any normal equation. I would move my smaller 14 cosine x over to my larger 14 cosine x, just like I would do it with solving equation. So that gets me 4 cosine x minus 7 is equal to negative 5. Add that 7 to both sides. So I get 4 cosine x is equal to 2. Dividing out your 4 means we're looking for a horizontal displacement. So what angle has a horizontal displacement of 1/2? So again, if you think about it, horizontal displacement, so going over 1/2 would work in both quadrant 1 and in quadrant 2. So if I'm going over 1/2, that means I'm going up higher. So I'm going up pi over 3, and I'm going down pi over 3, or this would put me at 5 pi over 3. So again, we're just going to stick with those positive values when I'm doing my general form. So my first set of solutions are going to be every rotation of pi over 3, so 2 pi n. My second set of solutions are going to be every rotation that lands at 5/3 of a pi. Again, where n is an element of the integers. Okay, get out your calculators for example 4. In example 4, we want to use a calculator to solve the equation, round our answer. So we are going to figure out where does our tangent function equal to 5. So pulling out your calculator, we're going to go ahead and graph. Let me just make sure my stat plots are all off, which they are not. Okay, so y equals, oops, we got some stuff in here. We want to see where does your tangent x equal 5. So I'm going to put tangent x in my first line. Oh, but I just realized I have mine dotted. Let's make that not dotted. There we go, make it solid. Make sure that your mode is in radians. right? And then let's do a zoom trig. So number 7, and see what that ends up looking like. Can I see my 5? I can't see my 5, so I need to either do a zoom fit or just extend my y maximum up to, like, let's go 9. There we go. Okay, so we need to let's find the first positive intersection. Looks like it's going to be right there. So I'm going to do second trace, number 5, intersect, enter, enter, enter. And it looks like we're intersecting at 1.3734008. And I would imagine then that my next intersection would be a full period over, and then another full period over, or full period back, full period back. And we have to remember that the period of a tangent function is pi. So for our answer, we're going to say that x is equal to 1.37 plus pi n. Again, where n is an element of your z's. So if we wanted to get the first two, my first one would be at, what you said, 1.37. The second one would be at, so doing 1.37 plus pi puts us about 4.51. Would be those first two positive intersections. Okay, let's go ahead and graph B. So getting out our calculator again. Where are you, calculator? There you are. So we're graphing now a cosine of x. And we want to see when cosine is equal to 0.6. So again, we can either do a zoom fit, a zoom trig. Let's see if we get it all in there in the zoom trig. I can see it. So we want to find that intersection of our first right here. So I'm going to do second trace, intersect, enter, enter, enter. It should give me that first one. So it looks like that first one's landing at 0.93. So now I have to think about it. If I do a full rotation, so it would land me right here. So I'm missing this guy right here. So I need to figure out what that second possible starting point is for my x value. So we're going to do another second intersect. I'm just going to move over so I force my calculator to give me that one. Oh, nope, I didn't go far enough. Let's try it again. Force it over here. There we go. Enter, enter, there it is. So 5.36 if I go to 2 decimal places. So for our answer for B, our first possible, we're in theta world, our first possible theta is about 0.93, and then every possible rotation of 2 pi beyond that. And then my second solution is 5.36 plus every possible rotation beyond that, again, where n is an element of the integers. So tangent, I only had one possible thing I needed, right, because it just shifts itself every period. But because of the cosine, we're going to have 2 intercepts happening. That's why we'd need to have 2 different variations of the general form. Okay, let's move on to part B. So in part B, we're going to turn our focus to finding solutions of trig equations and make our equations a little bit harder than just adding, subtracting, and dividing steps. So now we're going to get into factoring and maybe potentially doing different types of quadratic work with them. So we're just stepping up our games. So we're going to solve these following equations using our square root techniques. Now, if it really confuses you to have the sine and the cosine and the tangent functions in there, you can use what's called U substitution. So I'm going to do U substitution just to start out, so it kind of helps your brain figure out what it is that you're supposed to be doing. And then maybe you can just eliminate the U substitution and just jump right into factoring with the actual trig expressions in them. So if we let U equal whatever it is that you have happening to your trig equations, I'm going to let U equal sine x squared, or let's just actually let it equal just sine x. Then this whole expression becomes 4u squared minus 1 equals 0. So if I solve that equation for u squared, I would get u squared is equal to 1/4. Undoing a square means we have to square root it. So I'm going to get u is equal to positive and negative Square root of 1 is 1. Square root of 4 is 2. So that means u can equal either negative 1/2 or u can equal to positive 1/2. Now, what did we say our u is equal to? Sine of x. So now I'm going to turn my u into sine of x. And now I have two basic equations that we should be able to find the answers to, right? So when is my sine at a negative 1/2 displacement? Running out of space, I'll go over here. So vertical down negative 1/2 means we are wider. So that's going to be my pi over 6. But then I also need to get positive 1/2. So I'm going to have so pretty much every 1/6 of a pi is where we're going to be equal to. And luckily, we just want our solutions for one full rotation, so I don't need to do that general form. So my answer is going to be at pi over 6. And then the next would be, so 2 pi over 6 would be a third, 3 pi over 6, 4 pi over 6, so 5 pi over 6. 6 pi over 6, then 7 pi over 6. 8 pi over 6 goes to a third. 9 pi over 6, and then where are we at? 11 pi over 6 would be the next one. So those would be all of your solutions for when 4 sine squared x minus 1 would equal to 0. That's using u substitution. Now, you don't necessarily need to use u substitution because these are a little bit basic. So let's try to do it without in b. So if I just solved for the tan squared by itself, then I would end up with tan squared x is equal to 1/3. Square root both sides. So then we're looking for when does the tangent of x equal 1 over the square root of 3, plus or minus, which is the same as plus or minus root 3 over 3, right? So root 3 over 3 is not as steep as root 3, so it's going to be our 1/6 of a pi. Again, go figure. And since we have plus and minus, it's going to be all of those 1/6 of a pi, so pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. Okay, let's go to example 6. So now we're going to get it a little bit challenging because in example 5, we were just given one expression with a trig function in it, or a trig expression, I guess. In example 6, we're going to turn these into quadratics. So again, I'm going to do u substitution, just so you can see the quadratic within it. So whenever you have a trinomial, let's say, I'm going to let u represent whatever that middle term is. I'm going to let u equal sine of x. So then this expression becomes 2u squared minus u minus 1 is equal to 0. So that should be factorable. If it's not, then I'd have to use the quadratic formula, which we all know how to do. So factoring it, 2 times negative 1. So 2 times negative 1 is negative 2. Factors of negative 2 that get us to negative 1 would be negative 2 and 1. Put it over 2, reduce, attach my u's to the denominator. So we get u minus 1 to u plus 1 is equal to 0. So then we're going to have our u equal to 1, u equal to negative 1/2. So what was u? U was sine of x. So we need to figure out when my vertical displacement is 1 and when my vertical displacement is negative 1/2. Well, my vertical displacement is 1 at half a pi. And my vertical displacement is negative 1/2 down in quadrants 3 and 4. So 7 pi over 6 and 11 pi over 6. So those would be your 3 solutions just within one full rotation. Do the same thing for b. Turn that into u's. U is equal to cosine x. So we're factoring 6u squared minus u minus 2 is equal to 0. 6 times negative 2 is negative 12. Factors of negative 12 that get us to 1 would be negative 4 and positive 3. Put it over 6. Reduce. Negative 2/3. 1/2. U's attached to the denominator. So 3u minus 2. 2u plus 1 equals 0. So u is going to equal 2/3. Or u is equal to negative 1/2. My u was cosine, so we need to figure out when cosine x is equal to 2/3. So that's going to be a calculator thing. So I have to do cosine inverse on 2/3 on my calculator. And that should get us about 0.841. And then cosine is also positive down in quadrant 4. So if I do, all right, so let me erase this, get some space over here. So if I have cosine inverse of 2/3, so 0.84, that's going to put me in quadrant 1, because half a pi is like 1.57. So 0.84 is, let's say, right here. But I also have a positive cosine in quadrant 4. So now I need to figure out, you need to go down negative 0.841. I don't want my answer as negative 0.41 because I have to be between 0 and 2 pi. So I'm going to do 2 pi minus 0.841. And that's going to get me this angle in the positive. So that gets us about 5.442. And then we need to know when cosine is equal to negative 1/2. So cosine is negative in quadrants 2 and 3. So horizontal displacement means we're up higher, so 2 pi over 3. And then my last one would be down in quadrant 4, so 4 pi over 3. Or sorry, yeah, quadrant 3, not 4. Okay, I'm writing too big, I guess. So again, you don't need to use substitution. You could just jump right to 6 times negative 2 is negative 12, or do it, factor however you factor. This is how I factor. Negative 12, my middle term is 1, so negative 4, 3, put it over 6, gets you to that negative 2/3, 1/2. So instead of u, we would just go right to 3 cosine x minus 2 times 2 cosine x plus 1 equals 0. And then that would get you to cosine x needs to equal 2/3, cosine x needs to equal to negative 1/2. Okay, I don't care how you use it. Use substitution simplifies it and make it easier for you to see what you need to do. Or if you don't need it simplified, then just jump right to it. So in example 7, we have multiple functions happening here. So we got sine squared x tangent x equals 2 tangent x. I'm going to shift everything over to the left. So I get 0 on the right. So sine squared x tangent x minus 2 tangent x is equal to 0. And again, we're going just one rotation for my answers. So then I'm going to factor out a GCF of tangent. So then I get sine squared x minus 2 is equal to 0. So now using your product property, either your tangent of x needs to equal to 0 or sine squared x minus 2 needs to equal to 0. So my slope of my terminal ray is 0 at 0 and, no, the slope of my terminal ray is 0 at 0 and pi. Are we including 0? Do I have equals 2's up here? I do. I'm not including 2 pi though. So just at 0 is when we have a slope of 0. And then when does sine squared x equal 2? So sine x equals plus or minus the square root of 2. Well, the square root of 2, does that exceed our 1? I think so. Get my calculator out here. Square root of 2, oops, clear. Square root of 2 is 1.4. So this does not exist because it exceeds our negative 1 to 1. So my only solution is going to be 0. Oh no, we are at 0 and pi. What am I talking about? I forgot pi. Don't forget pi. So 0, comma, and pi. There we go. Okay, forgot my pi. We're flat at pi too. Okay, so as we continue solving more difficult equations, we're going to remember that you can use a graphing utility to check your solutions of these equations. So you can graph your left side in y1, put whatever it is in your right side. You don't even have to manipulate anything into y2. and then you can just look for where they would intersect. So for example, if I wanted to sine 2x equals 1, I would just get my calculator out. There it is. And then I would type in sine 2x in my first line, because that's the left side, and then I would type in 1 here, and then I could do a zoom fit. Is zoom fit 0? I think so, yeah. And then I could see where, I don't like that. Let's try zoom trig. Ooh, looks like we gotta zoom in there really good. So sine 2x is equal to 1, and then I'm gonna zoom in so I can see what's happening over here a little bit better. Looks like it's topping it out. Enter. Yeah, pretty much. Okay, so if I wanted to find the intersection, enter, enter, enter. Looks like we're intersecting at 0.78539, right? So we could do that just by typing it in. So if it's really complicated, we can always default to checking our answers with our graphing calculator, if you are allowed to use your graphing calculator. So x over 2, and we want to see when this is equal to the square root of 3, zoom trig, and then again we can find our intersections, right? Okay, so now let's see if we can do it by hand. So solving equations with multiple angles. Okay, so let's go ahead and start with example 2. Notice now we have not just an x with our tangent, we have a 2x. I'm gonna ignore that for now. I'm gonna solve it just like we normally do solve it, because let's do what we're used to. So I'm gonna do a tan inverse of root 3 and equal it to 2x. So we have to think about, well, what angle do I have my slope of my terminal ray at root 3 over 2? It's higher than, root 3, not root 3 over 2. It's higher than root 3 over 3, so that's going to be pi over 3. But it also is going to be the same slope down here in quadrant 3, which would be 4/3 of a pi. So normally we would say theta is equal to pi over 3, and it would be equal to 4 pi over 3, right? But now we have not theta, we have not x, we have 2x. So 2x is equal to pi over 3 and 4 pi over 3. So if I get x by itself there, then we have pi over 6, and then 4 over 6, so that'd be 2/3 of a pi. Now let's go back to the top. We needed to solve this on the interval from 0 to 2 pi, right? So right now, let's think about 2 pi being in 6, right? So 2 is the same as 12 pi over 6. Is everybody okay with that conversion? So notice where my answers currently are at. I'm going from pi over 6, which is in quadrant 1, to 2/3 of a pi, which is in quadrant 2. So I didn't find all my answers because I need to go a full rotation. So now we have to think about, well, what would be the equivalent of pi over 6? So if pi over 6, yeah, let's go over to this unit circle. If pi over 6 is here, what would have the same slope, the same terminal ray? Well, that would be, what, 7 pi over 6? And then what would have the same slope as 2/3 of a pi? So 2/3 of a pi is here. So 2/3 of pi, so this would be what? It would be 5/3 of a pi? Nope, 5, oh my goodness. Yeah, 5/3 of a pi. And then those would be all of your answers from 0 to 2 pi. So we get our first initial easy ones by doing this step right here and just dividing it out. But then that's only going to give us half of our solutions, right? Because then I have to think about, well, if I have those on my unit circle, what other values on that unit circle would get me the same either horizontal or vertical displacement or slope of your terminal ray. Okay, let's go ahead and try number 9. So here we are going to solve sine of x over 3 is equal to 1/2. So we're going to do the same thing. The sine's isolated. It's all by itself. So let's go ahead and do a sine inverse. Oops, I'm in highlighter mode. Sine inverse of 1/2 is equal to x over 3. So where do I have a vertical displacement of 1/2? So that's shorter. So we're at pi over 6. And we would also have a vertical displacement of 1/2 in quadrant 2. So that would be pi over 6, 2, 3, 4, 5 pi over 6. And kind of give myself some space. So instead of x equaling that, we're going to have x over 3 equaling that. So multiplying out your 3 to both sides is going to get me x is equal to 1/2 a pi. Then over here, multiplying by 3 is going to get me, what will that be, 5/2 of a pi? So x is equal to 5/2 of a pi are my two initial solutions, right? So now we need to think about, if I'm dealing in halves, right, from 0. So I always like to convert my interval here to have the same denominator, or the largest denominator. In the case of the last one was 6, because sometimes you might have like 12 in your denominator, so then it's easy to think about it as in twelfths. Okay, so we're going from 0 to 4/2 of a pi. So I guess we need to ask ourselves, did we go far enough? Nope. Yes, 4/2 of pi is 2 pi. So 1/2 a pi works, yeah. 5/2 of a pi goes beyond, right? So my only solution that's going to fall within that interval is 1/2 a pi. All right, and there is our answer.